So chapter 1 is introductions and so chapter 1 is about the fundamentals of this. Let me open up my So this covers our textbook chapter 1, and that is the outlines of the sections. And again, this section pretty much follow our the newest versions. And for example, 1.3 and 1.12. If the section number I didn't list it, that means I'm going to skip, okay, and for a few reasons. So for any sections, if I wouldn't cover it in the lectures, that won't be covered in the test or exam. Kind of give you this kind of information. Okay, now the brief history, and let me quickly going over this one. So the dynamics of this kind of discrete system basically can trace back to Galileo, right? So here in his first treatise, that means the small book or thesis is on the modern dynamics is in 1590s. And basically that one, he developed some kind of work, the preliminary work on the oscillation of the simple pendulum. The simple pendulum basically like this, okay, and small oscillations. And he described that one, and basically back to then, there's no differential equation developed yet. And I believe this time is before Newton's. And you know the DFQ was developed by Newton. So back to then, everything is pure algebra. Okay, so that back to then, if you really have time, when I was a PhD, I kind of interested in digging out his treatise and different topic. And the written is a very, very different language in terms of the math, and everything is geometry, algebra, and then draw a lot of the different kind of weird things. But that is the way they do that one. So he basically, that is the first, the kind of the clear work on the modern theory of vibrations. And this device basically is the kind of this the apparatus. And that kind of sit onto the ground, and whenever there's the earthquake or seismic vibrations from the ground, then this bar will tilt it, and in a way to trigger the mechanism. In the way the small metal ball being kind of the hold in the mouth of the dragon head will be open and then come down. So in this way, that help people the direction where the systematic earthquake they're coming from. So in this case, that's supposed to come to that direction. That is the instrument in the ancient Chinese, the kind of the techniques development. Usually they have the kind of the apparatus in. They have the dragon in put into the 12 different directions. So basically 1, 2, 3, 4. So they put into the 12 in this way. Every 30 degrees they have such a head. So that means they can tell, okay, that is the source of the earthquake coming from that particular direction. So that's the way they're doing that one. And right now they can. When I was at high school, I went to a museum, and I came from Taiwan, Taipei. And there's a museum in Taiwan, and there's a spatial, I remember the spatial exhibitions about the ancient technology of the China. So I remember that one, the people rebuilt this one, and pretty neat. And the mechanism, I could pay attention to the mechanism here. Basically, that is linking to our, we call the 4-bar linkage, right? Have you been learned that one from your ME 302? Yeah, basically that's a very elegant design of a 4-bar linkage. In that way, the sensitivity of triggering from the oscillation of this middle bar to trigger the open up of the mouth is very sensitive. So in the way they can adjust, and then they can tell even the small vibrations, then they can see. Okay. This one is another word. So this is a simple pendulum, and then they kind of oscillating, projecting onto the base area into 360 degrees, and that one is by coulombs. This one I believe in high school. I think in high school we always have learned in. I remember at least my learning. I have a kind of small section to do the calculation for this one. This is the modern one, and this is the, I don't know whether you heard this story. This is the new bridge. I think it's in Washington, right? I forgot, but here is a link provided to you. We can try to open it up, see. And that is called the fluid structure interactions, and to cause the resonance of the structures. And you can see right now is in away from his integrity, and because the wind kind of blowing through, interacting right now is approaching to its resonance, which means approaching to the natural frequencies of the whole structures, kind of weird, and eventually if the structure cannot hold his integrity, basically damage. So that's a way. And this happened just a few weeks or few months after the bridge was built. I remember this whole story. And right now this kind of things, and I think there's a sound. Okay. So this is a way not that the wind is so strong, but however the wind interacting with the structure and vibrating near its natural frequencies. And once we call it vibrating near the natural frequency, what we call the resonance, we will talk about this term later, and that system by itself just go to unstable. Okay, so eventually going to collapse. Yeah, so we can continue probably. Almost done. Get it quicker. Okay, it's done. Okay, so it's not the same, the wind is so strong, but however the wind induced vibration of the structure is nearby its natural frequencies. So by itself the system will become very unstable. Okay, and later on we will have the introduction about the resonance. Okay, so let me turn off this one. Okay, so that this concept tell us the that kind of Tacoma, yeah, in Washington. I believe it's about the Washington. You can read the stories from the internet. Okay, this one is a kind of schematic descriptions of a modern machine tool. And basically this is the list tool, the milling machines. And those machines, I believe from machine shop, you should have seen, even we have a CNC machines. And those machines in particular in defense, in application to defense industry, or even sometimes in automotive industry, they asking the precision of the machining be high. Okay, so if say they want to have the very high precision of the machining components, one way to do it is to reduce any system-induced vibrations or system interacting vibrations. That means you have to make sure the ground, the vibrations from ground or any motion from ground transmitting to the machine here should be reduced. The second one, when the motor is beginning to spin, and that is a system-induced the mobility. That one, the motor, any motor-induced vibration, that means about the system structure per se, that one must be reduced as well. So most of the time, again, for the high precision machining, they simply want to buy any effort using passive or using active control to minimize such vibration, unwanted vibrations. Okay. To do that one method is through the simulations. They can simulate the whole machines in terms of the finite element software. They can from there to simulate and then to find and try to find the kind of the knowledge or understanding about the system before they really physically to modify the machine. And again, this topic is still hot nowadays. And America has the such an industry, the machine industry, and Taiwan, Japan, they have this kind of machine industry. They're still doing the things. And right now, they since this kind of the control dynamics and control work in for pertaining to this kind of the work, the companies they kind of a little bit stretch their business into robots. Right now, the robots. Have you heard about the for example, one company, Boston Dynamics. From YouTube, you see a lot of the robots, kind of the humanoids like the robot or dog, cheaters. So basically, those one is the example. So the company making this kind of the things, the trend I've seen is kind of stretched into kind of the robot. Because the same concept and the motors, but simply the different, I would say, the shape, the outlook of the structures here. Okay, and so kind of provide you this, and this one is another example of where the vibration can be applied. So in this slide, I show is on the analysis of the wings of the airplane. And you know the airplane, the wing, if you sit by the windows nearby the wings, sometimes you see when they go through the turbulence, very scary. You see the wind, you can see using your bare eyes, the wind really is kind of flipping. Weird, scary, very scary. Have you dared see if the wind broken, what would happen, right? Don't worry about this one. The big company like Boeing or Airbus, they will guarantee they call the reliability or lifetime. Say flying so for how many hours, then you have a risk. But before doing that one, the airline companies will take care of the kind of maintenance already. So for the companies like Boeing or Airbus, they design the things and they want to analyze the structure. The safety, for example, the dynamics per se, vibrations. Again, they put into finite the element simulations, and do the simulation and analyze the vibration modes. And this is called the multiple degree of freedom. Very complicated, high number of the multiple degree of freedom system they can put into simulations. And then they see, okay, for example, the red one usually indicating is the highest number of something. For example, the force or displacement, etc. Depends on. I don't have that kind of information for the simulations, but they using this kind of techniques in terms of simulations. And on the other side, if you have been doing or hopefully you will have chance to work as intern for Boeing, I've seen is they do the physical testing. The way is this: they're using the true scale model of the airplane, and they want to test the vibration or structural integrity of the wings. They hang the different back of the sand of the different mass, different weight at the different locations. Okay, to simulate the static loading, and then they begin to using certain motor or something to begin to drive the wings to vibrate. So study the vibration of the wings on the different loading, and that's the way they do the physical testing in the way to they extract some information. Okay, so that is one example here. And so that is the machine, and for example, this is a car, say a truck. This model, basically, they're using the discrete model, and this model being used quite a bit common in automobile industry. Basically, they use lump mass, they use lump spring, and they're using the lump kind of damper. And different car model have a different know-how, and that is a business secret. So, for example, for Toyota or compared to the for torques. Those kind of the numbers of this one and how the setup is. Again, that's the secret. The company is using this kind of discrete model to proceed and analyze, and then before they're doing the real testing. Okay, so kind of show you in this way. So probably today we stop at this page, and then coming back Wednesday.